Yep. Well, hey everybody. I'm glad to see a lot of faces right now. Well, I really appreciate your presence here. I'm Sebastian Arias. I'm a software developer from Ecuador. So today I'm going to be sharing with you Pythonic laziness and how to unleash the power of generators. Yep, about me, I'm a software engineer. I've been working for Stack Builders, that is a software consultancy in New York, for around 5 years. This time I've been doing Python and some other languages, but I'm really an enthusiast in Python and also functional programming advocate that's been part of my career since the beginning. And also, in my free time, I love traveling and discovering new cities. So a fun fact is that it's my first time here in Prague, and I'm really enjoying it. Well, let's see a little bit of the overview that we are going to be covering today. Um, in this talk, we are going to be discovering how lazy evaluation works and also how we can leverage this with generators in Python. So we will learn a little bit of lazy evaluation, we're going to understand it, and also we're going to be checking some real-life scenarios where I've been using this approach to improve performance in memory and execution of my programs and scripts. So, first of all, let's jump with the principles of lazy evaluation. So, first of all, what is lazy evaluation? Lazy evaluation is a programming technique where the expressions are delayed until they are needed. So we don't execute scripts or variables in real time. So they are delayed and evaluated just when they are needed or required. So how it is differ of eager or static evaluation, that it's the most common concept that we use in our daily basis. So laziness, as I mentioned, computes expression only when the value is required, meaning that we are deferring all the computation until the specific moment that value is going to be used. And also, the result is cached for future uses. So we have this kind of improvement at the time of using memory. The first differences with eager evaluation is that in eager evaluation, as soon as the value is kind of bounded with a variable or executed, it's going to be using memory spaces. So when lazy evaluation is useful. So let's see some scenarios here. Lazy evaluation is really useful when we have expensive or time-consuming scripts. And also, by deferring the evaluation until it is necessary, we can improve the overall performance of the application. So, where is lazy evaluation used? First of all, in functional programming. As I mentioned at the beginning, functional programming has been part of my software development experience. So I'm really eager you to also check it out if you haven't had in the past. So lazy evaluation is used, for example, in a pure functional programming language called Haskell, where it's a central feature that it leverages the software, the scripts there. Also, talking about functional programming, we have to talk about purity. So, since generators are really pure and leverage from lazy evaluation, you prevent developers to cause side effects and other type of these changes that might not be wanted. So, we enforce developers to use purity and also to prevent the side effects on the code. And finally, but not least, is code efficiency. By writing generators, we will have structures that are concise and easy to maintain. And also, we unblock this new feature that will be potentially having infinite data structures, since we are not storing all the elements in memory. So, to understand a little bit of lazy evaluation and how it works, I have prepared a small code snippet here, as you can see, that is some code snippet in Haskell. Basically, what we are doing, we're instantiating here a function called LazySum that basically has elements of type number, and we're using them, or we're expecting to receive a list of them. Then we're going to have this element, A, as the result or the returning type data that we have. And for this LazySum, I've done two scenarios. The first of all, LazySum, when it's receiving an empty list, I'm going to be returning a 0 because we have nothing to add. And another scenario, when we receive a list, basically what I am doing here is taking the first element and also the rest of the list that we are receiving, and evaluating the first element, and adding and doing it recursively to submit the rest of the list into lazy sum. Basically, here we have how a lazy evaluation works. So what we're doing here is using our lazy sum function, passing a list of numbers from 1 to 3, and evaluating them with the rules that we specified earlier on. So first of all, we're going to have number 1, right? Because we're using this pattern, right? We have a list. We're going to take the first element and the rest of the list and do this recursively, right? So we're having 1 as the first element, and then in lazy sum we're passing the rest of the list. We're going to do this iteration until we run out of the items. So in the second iteration, what we're going to do is call the rest, right? We're taking the first number 2, and then recursively call the rest of the list. And finally, we're going to have the last number that we have in the list right here, and calling lazy sum with an empty array, since we run out of items. And at the end of the day, we're going to end up with this expression, right? We're going to have 1 plus 2 plus 3 plus 0, and then we're going to be expecting this the result. So what we are doing here is delaying all the computation until we need the real value, right, as we have it here. So that's basically, in a nutshell, how lazy evaluation works. So, oh, there we go. Yeah. How does lazy evaluation works in Python, right? We are talking about the concept now. Let's apply it in Python. So we have an iterator function. So basically, expressions that are typically grabbed in lazy data structures are functions that are going to encapsulate the functionality itself until it's called. Then we're going to cache the result. What does this mean? Since we're having invocations, this time we're going to be caching the result that we have and then iterating over it until it's needed and for future use when we are yielding or returning this type of elements. And finally, how do we do this in Python? As you can see there, we leverage from the yield keyword. Most of you maybe have used yield keyword if you are used to use this in generators or maybe coroutines. So we leverage from this keyword. Here I have an example of a lazy sequence that basically is an infinite structure. Basically what's doing is going to be returning a number that it's sequentially being executed and generated until the condition is false. In this case, since I am using a while through, this is going to be infinite, right? What's happening here? We're instantiating our sequence right here, and what's happening when we call the next function that comes from iterators. Basically, what it is doing is starting to execute letter I, that we are assigning a 0. Since the condition is true, it's going to be yielding the value of 0. And we are caching this value for future use, right? The next time, in line number 9, we are calling the next iteration that is going to remember that we yield 0, and it's going to add 1. Then we're going to the condition, and it's going to be yielding number 1, and so on, and so on, and so on. So here we can see how values are cached for future use, right? So how can leverage lazy evaluation for a better performance and memory usage? Here I'm doing some comparison between memory efficiency and also optimizing performance. So let's see. First of all, remember that generators are going to generate values on the fly. This meaning that values are going to be generated just when they are needed. So in this example right here that I have right here, basically I'm using a timeit and a memory profiler or line profiler to gather some information related to memory usage and also to the changes that we are doing since we are kind of expecting some stuff. So first of all, we're going to check the code right now. And the code that we have, it's right here. So what we are doing right here. Basically, what we are doing is a generator, as you saw early on. we're kind of doing just 1 million of numbers, right, with the range function, and we are yielding them over. Also, if you love type hints, as I do, you can see that we can leverage from type hints. Here you have the generator type. And also, since we're just using generators, we're going to be yielding a new number, right? These two other parameters are basically for coroutines. If you are used to coroutines, you can check them out. But as you can see, it's really straightforward, right? So we're creating a range from a data generator, and we're going to be using that in other ways. For example, I created this function that it's called it's even, just to double check something on the list that we have. So as you can see, basically what we have here is no memory increment from the memory usage and when it's executing this script. And other thing that you can see is that we are having 1 million of occurrences. We are not using extra computation or extra kind of stuff just to generate the data or the list that we have there. So basically, we have no memory overflows. We don't have to do, for example, a try and accept execution there to prevent memory leaks and stuff like that, right? And also something incredible is that in spite we're using 1 million of elements in this generator, the time is really fast, right? Like 20 seconds for 1 million elements iteration. It's really fast. Also, we're going to be comparing this with an eager evaluation. As you can see here, we're going to be using or leveraging from list comprehensions that are really optimized for Python development. In this scenario, as you can see here, we have the first difference. Do you remember with lazy evaluation, we have 1 million occurrences at the time of creating data? Here, in this example, we are reaching 2 million of iterations. Why is this happening? Basically, because first of all, we have to instantiate the list that we are going to be using. Also, we are going to be allocating this in memory. And as you can see, the memory usage increments from 20 megabytes to 66 megabytes. That is a huge leap. And also, after the memory usage, we're going to be using 9 megabytes to store it in memory. And also, at the end of the for loop, we are also calling our isEven function to determine if the value is even or not. And we're calling, once again, this 1 million times of occurrences. At the end of the day, we're doing 3 million of occurrences for the same script that we generators. We just hit 1 million each time. So, as the differences, we're kind of having a slower time of execution. So what are the results basically on this first comparison? We're having 3.1 times less memory usage for the same use case, and also it's running 1/4 times faster. And now let's see the performance optimization that we can do with generators. As you can see, generators leverage the use case of kind of reaching certain conditions that need to be met. So as you can see, we can enhance recursion. But basically, enhancing recursion is going to be a different topic and maybe a different talk. So we are not going to be deeply here. So what's happening here? Now I just updated the functionality, and instead of just checking if the number is even or not, we're going to be adding all the numbers generated. So we are adding an extra step in our process. So for this, as you can see, the generator is just occurrence in 1. Since it's lazy, it's just allocated 1 occurrence in memory, and then it's going to be looped in the sum function. That is the built-in function that we have in Python. So this whole process to get the result of adding the even numbers for a million occurrences and adding them took less than a second using generators. The same scenario for eager or static evaluation. As you can see, I'm always using the list comprehension and also adding the if clause there, and then adding all these elements took around 9 seconds. Also, if you notice, we have also an increment in memory usage, and in lazy evaluation, we have no increment in memory. So what are the results here in terms of performance? Basically, we use 2.1 less memory for the same use case scenario, adding an extra functionality. And also, it was almost 17 times faster. So you can see the improvement here. So now let's get started with generators in Python. So basically, as I mentioned, I'm going to be a little bit fast because we're running out of time. And basically, generators are a type of iterators. Basically, they are an iterable, just like tuples or lists. It generates values on the fly. As you can see, they do not store each of the values in memory. They basically yield these values when they are needed and are memory efficient, and they prevent memory overflow, as we saw on the previous example and comparison. So how do we define generators? As we saw earlier on, we are leveraging from the yield keyword and also using the def to define a function for the function generators. And here what I did was basically create my own range functionality. As you can see, we are kind of mimicking the same functionality of range function. And one important thing that I want you to check here is the type of the variables that we have right here, right? For example, my custom range, that is going to be the generator, if I am asking the time to Python, it says that it's a function. We are not doing nothing else than a function right here. And also, when we instantiated and initialize the generator in my range a variable, as you can see, it's a class generator. So basically, it's an object that is going to be a generator. And also, one important thing is that we can leverage from building functions like next or for loops to loop over all these elements, since it's an iterator, so nothing weird there. Also, you can remember the yield keyword as the keyword that is going to generate or produce the values that we're using on our generator. So basically, remember that the body of our function generator is not going to be evaluated right away. So it just returns the generator object that we can iterate over to our use cases. So for using a generator, we can use for loops, as I mentioned earlier on, or leverage from the next function of the iterators, as you normally do in lists or tuples. And also, one thing that I really like from here, we're really used to use comprehensions. And we have a syntax sugar type of comprehension here for generators. That is, instead of using square brackets, we use parentheses to create our generator right away in a one-liner. For example, I have here a square generator that is basically doing the square of all the elements that we have. So as you can see, we have the same type of class generator as we did on our function generator. So that's something really useful for one-liners. So what are the advantages of generators? So we have memory efficient. They are going to be saving as memory at the time of execution. Also, we leverage from lazy evaluation, so we are delaying all the computation until the values are needed. And we unblock this kind of a feature that is going to be infinite sequences. Since we don't run out of memory, we can use these infinite sequences on different use cases. And also time efficient, as we saw in the comparison between lazy evaluation and eager evaluation, time efficient is really, really useful. So let's go to some practical examples. So we're going to be checking large datasets. Basically, what I want to show you right here is this large dataset that I'm using right here. So basically, we have a CSV file with 1 million of items. And what we are doing is this comparison. So basically, we have a file reader here, as you can see, that it's yielding row by row from the file. And we have this loop that we can implement some functionality. For time being, I'm not going to do any functionality right now. But we can see the same use case with eager evaluation, or a traditional way of doing this with a comprehension to have an iterable to loop in row by row from the CSV. So the comparison here in terms of performance and memory usage is that using the generator approach, as you can see, we have similar scenario like with the first comparison, but now we are kind of looping through information through a file that has a lot of stuff As you can see, basically, we don't have a memory increment after running this program. And as you can see, I'm using here some memory login for checking the memory before and after the evaluation. And also, as you can see, the time of execution is really, really low compared with what we have with eager evaluation. For example, using the list approach, as you can see, we have a memory increment that is huge compared to the previous one, since we are allocating all these CSV rows in memory. And also, the execution time is not the best. So what happened here? Basically, we're being 38 times faster with using generators approach instead of allocating these rows in memory. And also, it took like less than a second to generate the data and to loop over it. So we can see huge performance enhancements here. And last but not least is the sequences. Here's not comparison, since we can have infinite sequences allocated in memory because we're going to be restricted to the memory of the server or the computer that we're using. And with generators and lazy evaluation, we can have potentially infinite sequences compared to this. So this is something that we can compare. So it's kind of a huge improvement in terms of functionality. So basically, here are some conclusions that I have in my experience of using generators in most of my projects. So generators are really, really powerful tool for performing and flexible programming. We have some enhancements in terms of maintainability and also reducing side effects and having purity in Python. Also, generators save memory and improve performance. And with Python, they are really easy to use with this syntax sugar example that I share with you as comprehensions. And finally, I think that we completed the goals for today. That was understanding lazy evaluation, also discovering how generators leverage from lazy evaluation. And also, we unveiled some of the performance and efficiency enhancements that we have with generators. And finally, we understand the importance of lazy evaluation and how to leverage it for optimizing our daily Python code. So now we have this time for questions. And thank you for your attention. I hope this is right, correctly said. So thank you very much, all of you, for assisting. And feel free to reach me out. So feel free to reach me out. It's going to be awesome to share with you guys. And now I'm going to be asking for a selfie with all of you. Maybe if you can raise your hands, it's going to be awesome for my feed. So thank you very much, guys. I really appreciate it. So feel free to ping me or reach me out in the event.
Thank you, Sebastian. To start off, can you list some downsides of generators or situations where it's preferable to use eager evaluation?
Yeah, that's a really great question. This is something that I encounter on a daily basis. So generators, since they are yielding and generating values on the fly, we can access the indexes, for example, as we have in lists. In lists, our use case is to jump between position or indexes of an array, for example. Maybe it's a good approach to use that instead of generators. Also, when we are kind of having different functionalities kind of being chained, sometimes it's more performant to use memory allocation, since you just access the value instead of generating it. So yeah, there are kind of like in most of the things, there are good stuff and also some pitfalls that we have to consider depending on our use case. Mm-hmm.
Thanks. A bit off topic, but what did you use for the slides?
Yeah, that's a great question. This is called a gamma.app. That's kind of a great tool that I've been using for all my presentation of this type of tokens. It's really versatile, and I really encourage you to use it.
Thanks. Do you have some interesting real-world examples where using lazy evaluation can lead to significantly cleaner code?
Yep. There are a lot of stuff for using generators or lazy evaluation for cleaner code. One of the latest stuff that I've been working recently was we were have some performance issues in terms of database gathering information. So I created a cursor that is yielding the values from, I think it was like 100 million database stuff in the backend. So that increased the performance, and that was one of the recent use cases I use or leverage from lazy evaluation.
By the way, if you have a question you want to ask, I'll right there. In the meantime, any tips on testing generators properly?
Oh, yeah, that's a really good one. Related to testing, well, they are, since this is pure, we don't have to kind of test different or not the happy path, so we can leverage this purity stuff.
Hello, thanks again for the speech. I would like to ask for the values that are being generated. So you said that as the generator kind of generates the values on the fly, I'm curious what happens to them later on, because you said there is no memory bump. So the way I understand it is that on the next iteration, the previous value gets kind of discarded or deleted. Is this true, or is there some other way this works?
Yeah, well, under the hood, I don't know specifically how they are implemented under the hood, but in theory, what we are doing is generating a value. This is cache when we yield, and this is cached because we need this value to generate the next one, right? To do calculations and stuff. So once this value is already used, the cache is deleted, and the new cached value is the recently generated. That's why I'm saying that if we need to preserve these values in memory, maybe our use case is better for lists. But if we are doing, for example, this type of examples, or also we just need data to be generated on that time and not going to be used later on, we can leverage from generator. So it depends basically on our use case.
So one from Slido, why are people afraid of generators?
Yeah, well, I was afraid of a generator as well, and also from coroutines. I think that this is kind of a concept that is not easy to get used to, but with some practice and also with easier examples like the ones that I share right now, you get used to get these generated values also to be more comfortable using yield. Also, then just reviewing some theory with coroutines, you know that you can add some values to these coroutines and also with generators. So I think that coming from, for example, an OOP mindset, it's kind of easier to think on lists. But when we leverage from functional programming and read a little bit from the benefits that it comes, we're going to be kind of eager to understand these values with practice.
Okay, I have a question. You can combine together the generators to create like really interesting iterators. So I would like to ask if there is something like design patterns focusing on this kind of topic.
Yep. Well, a design pattern that we might have when leveraging from generators is piping. If you are used to do pipes, like for example, when you are using I don't know, a bash, and you have this straight line to concatenate different functionalities with the input from one command, the output of one command turns into the input of the next command. We can leverage from this piping scenario as a pattern. So, yep, I really encourage you to use it. So it's really interesting and easy. And once that you get used to this, you won't want to get back to normal iterators or something like that.
Thank you, Sebastian.
Thank you very much.